Good evening, students. Here we are on the sixth day of our 45 days crash course on chemistry for the upcoming JEE exam, and we were on the chapter that is chemical bonding. And today is the second day of this chapter. So we have studied in the earlier class about this Lewis dot structure, that how this Lewis dot structure was the primitive one, and the first one to talk about the structure of electrons and their distribution in a compound. Later on, the second theory that was developed was known as the Whisper theory. So this Whisper theory is the most important one for this. So before going to Whisper theory, let us discuss about the Fajans rules. So in the previous class, I always used the word that a compound is ionic to some extent or covalent to some extent, by which I meant that a compound is never overall ionic or not overall covalent. So various factors are there which decide that whether a compound will be covalent or ionic. So to conclude all those factors, so one of the rule which is given by Fajan is that it is based on polarization. So how it works? So he says that in a polar covalent compound, there is more electron density around the electronegative element. Yeah, it is true. So he says that due to this uh, means unsymmetrical distribution of charge, there arise some kind of covalency in the ionic compound also. So how does it happen? So it happens due to the electrostatic attraction of this uh, cation. So I will explain it using a diagram. So there is so for second point is that, so you must keep in mind that non-polar molecule never have this kind of Fajans effect. So what is this Fajans effect? So it is the diagram which describes it. So first of all, let us take an example of a ionic. So this ion you can see here that is cation and it is an anion. Now what happened is that you know that the electrons are not something that is localized, or we can say that okay, this electron is present here in this shell and in this shell, rather than it is delocalized. Means you can predict the probability of finding the electron at one place, and which will not be fixed for all the time, but it will vary with time also. So with respect to that concept, we know that the probability of the electron is changing from time to time in a cation, on an anion, or a compound all over. So if you take so it is an idealized case, so where the positive charge is localized here, means it is distributed symmetrically, and this negative charge is distributed symmetrically here. Now consider for an instance that this negative charge, means the electron cloud, are delocalized to this part of this cation. So due to this reason, all the positive charge will be on the right side, which is near to the anion. So what happened as a result of it? The anion, which is negative charge, so its negative charge is getting delocalized. Means what is means it, what do you mean by this? So suppose initially it has a shape which is perfectly symmetrical, and the negative charge is distributed all over symmetrically. Now, as this positive charge comes for an instant, it will attract the negative charge towards itself, because due to electrostatic force of attraction between these two, and it is distorted like this. Suppose it is distorted like this. Now, this negative charge will be here, means that a delta negative charge will develop here because of the attraction between this cationic positive charge, and similarly a delta positive charge will be accumulated here. Okay, now due to this reason, this electron cloud comes here, and not only that, it is shared between this cation and anion to some extent. Now you know that what is covalent compound. So basically in covalent compound there is sharing of electrons. So the same thing happens here, but not to that extent, but to some extent. Due to this reason, some sort of covalency is seen in this ionic compound also. So what this phenomena is explained by the Fajans rule. So many factors are there which decides that, yeah, which will be polarized, which will be what will be polarization, and what will be the size that will decide the polarization. So we'll see it one by one. So the first one is polarization. So we have seen the thing here that an ion is getting polarized due to the presence of cation, means it is getting distorted, and that phenomena is called polarization. Now second is the polarizing power. So this polarizing power is associated with cation. So it is the ability of a cation to polarize a anion. Next is polarizability. So I am dealing with shortly. So what is this polarizability? So it is the property of an anion to get polarized in the presence of a positive charge, of an instantaneous positive charge. So it is the ease with which an ion will get polarized. So these are the three terms related to Fajans rule. Now we will see how this polarizing power and polarizability of cation and anion changes with size and charge. First of all, the charge. So we know that this Fajans rule phenomena is completely based on electrostatic attraction, because the instantaneous development of positive charge on the right side, that is, you cannot say right side, on the side of the anion, result in the electrostatic attraction and distortion of the anion. Now further we can see that this attraction is mainly due to the presence of charge and electrostatic attraction. So you know that electrostatic force is directly proportional to square of the charges. So as the charge will increase, the cation will be more capable of polarizing this anion, means the polarizing power of cation will increase. So first is this. Now second is the smaller size of cation. So according to this, Fajan rule says that smaller is the size of the cation, it is directly proportional to covalency. Means the compound will be more and more covalent. So how is it so? So you know, so if a cation is smaller like this, and suppose we have a different cation that is large enough, and they both have the same charge, but since its size is large, it will be distributed widely like this. And since it has a small charge, this cation, smaller cation, it has the charge concentrated on a very small area. That is, its charge is to area ratio, that is the charge density is more as compared to this one. Now, if you see an anion here, if you put an anion here, that is negative charge, like this. Now, since its surface area is small, you know here it is small, so the positive charge will be accumulated more here. So this charge density will be more. So it will have an increased charge density. You know that there is an instantaneous development of charge. Now during this instantaneous development of charge, it will have a more charge density as its size is small. Hence, it will apply more electrostatic attraction to this negative charge and increasing its polarizing power. So the polarizing power is also proportional to the is inversely proportional to the size of the cation. Now the size of the anion. So larger anion. So if you have a larger anion, so this one is like this. So larger anion also proportional to covalency. So how is it? How is it? Let me show you. Covalency. Suppose you have a anion like this and an anion like this, which is larger in size. Now in both this anion, we have negative charge spread all over the place in the ion like this. But since this size is large, so this charge will be distributed more widely as compared to this. Now suppose you have to polarize this anion, means you have to pull this electron towards cation. But you can see here that the distance between the positive and the negative charge, because the size is small, they are held more tightly. This negative charge is held more tightly as compared to this one, because it is loosely bounded due to more separation of these charges here, means this distance is more. Okay, so due to this increase in distance, the negative charge will be held more strongly in this case. So if you want to polarize this, means you have to pull it, you have to apply more force as compared to this one. So the polarizability of this anion is more as compared to the smaller one. So this is the three factors we decided. So if we summarize it, we can write it like this. So according to Fajans rule, we know that covalency is directly proportional to charge on cation. Then again, directly proportional to 1 by size of cation. That is inversely proportional to size of cation, you can also say that. And directly proportional to size of anion. So this is the basic Fajans rule. So if you want to compare the covalency character, you will simply see the first of all the charge. So yes, one more thing here. So the important thing to mention here is that since that charge is the major factor, because we know that electrostatic force of attraction is mainly dependent upon charge. And why is it so? You know that we have to take the square of the charges as we write the formula for force of attraction. That is Coulombic force of attraction is directly proportional to square of the charges. So due to this reason, so if you have a greater charge, so it will automatically have a greater polarizing power. So that cation will have a greater polarizing power no matter what the size you are taking. So this is the thing here. Now let us move to next slide. So let us do an example to clarify our concept more clearly. This is a question based on Fajans rule. It says that you have to order this three compounds in order of covalency, which means which one is more covalent and which one is less. So I have told you earlier. So first you will see the charges. So this one has positive, Li positive. This is Li positive, F negative, Ca2 plus, that is 2 positive and 1 negative. Now you can see here clearly that Ca2 plus is having more charge. Yeah, it is correct. And then both of this which have a only unit charge on both of the cation. So this one will have a more covalent character. So the first one having the most covalent character is CaF2. Then next we have NaF and LiF. Between NaF and LiF, we know that Li has a smaller charge, smaller radius. So since it has a smaller radius, so it will have a it will have a more polarizing power. We have seen the previous slide also. So I have written the proportionality means relation. You have seen it clearly. So this LiF, due to its smaller charge of lithium ion, will be more covalent than sodium. Then we have the NaF. So this is the order we have here. Now we will move to the most important part of this lecture. Means you can say the most important means deciding factor of this chapter also, which is the valence shell electron repulsion theory, VSEPR, electron pair repulsion theory. So what does this VSEPR theory assume? So it has an assumption. So it has assumed something to describe the structure of a given compound that you have. So as we have seen in the earlier class that Lewis dot structure of Cosell-Lewis was not able to fully explain the structure of the given compound. So later on this VSEPR theory came upon, which was very means you can say very significant in explaining the given compound structure. So it has certain assumptions. So it takes the valence shell and we see the repulsion between the electron pairs. So we are only considering the valence shell, and then we see the repulsion between the electron pairs to describe this so-called structure of the given compound. So it will adapt to such a structure so that the repulsion between the electrons is less, or the lone pair bond pair is less. So here two type of electrons we are having. The first one is the bond pair and the second one is the lone pair. So what is the difference between these two? So if you have seen in the previous class, so if we draw for a H2O molecule, the Lewis structure for H2O molecule, so the O is the central atom here. It has 6 electrons like this, like 1, 2, 3, 4, 5 and 6. Now we have a hydrogen atom here. It is having one electron in the valence shell. So if we draw the Lewis structure, so we know that hydrogen needs one electron to complete its octet. Similarly, this hydrogen also will need one electron to complete octet. Now this oxygen will need two electrons, so it will take it from both of this. So it will be like this kind of fashion. Now you can see here clearly that this lone pair, this two lone pair here, are not bonded electrons. So this one, this pair, so 1 and 2, two pairs are present. So two lone pair are present, and bond pair are also two for this water. So these are the bond pair and the lone pair. Okay, so now they are arranged in such a fashion in the spatial, means the spatial arrangement is such that there is minimum repulsion between those electron pairs. Now we have a formula for deciding this shape. So how do we decide this shape in this using the VSEPR theory? So the formula goes like this. So it is given like this. So half. Then we have the number of valence electrons in central atom. So suppose we are considering for water, then the central atom will be oxygen. So we'll count the number of valence electron in that. Now next, plus the negative charge. So the number of negative charge we have, and plus the number of monovalent atoms. So you will add this use this formula to determine the structure of a given compound. So how is it done? So if you want, we can see an example to calculate Z. Yeah. So let us take a simple example, that is ammonia. So let us do it. Yeah, one more thing here. So it will be this formula will be changed. So I will see it later. So what is the central atom here? So it is a nitrogen, hydrogen. So I'm not doing again this Lewis dot structure. You can do it by yourself. So it is like this kind of thing. So now you see here that one lone pair is present here. So we will write here one lone pair. Number of lone pair is number of lone pair electrons is 2. What are the number of bond pair we have? So number of bond pair, or you can say number of monovalent atoms. So number of monovalent atoms, it is 3. Okay, so we have 3 monovalent atoms and 2 lone pairs. So and also number of valence electron. So it will be number of valence electron. So what it will be? So 2 plus 3, that is 5. So what is the formula here? So we have to calculate Z here. So Z is equals to, I'm writing it here right now in the upside. So Z is equals to half into number of valence electron, that is 5. So do we have a charge on this? No, it is 0. Negative charge is 0. Similarly, the positive charge is also 0. What is the number of monovalent atom? It is 3. So 5 plus 3, 8. 1 by 2, that is 4. So in this way you can calculate Z. So you can do it for different molecules and do it for your practice also. So once you are getting a grasp of it, then you can decide the molecular structure. So we do have a table here for doing that. So in the upcoming slide you can see that table. So I have calculated lone pair electron, because we can derive a formula for lone pair also if you want. So in many questions there in the JEE we do in the match the following questions in JEE advanced many questions. There is something called match the lone pair, then match the bond pair, then match the hybridization, and so on. So that's a different part. So I have calculated this lone pair also. So if you want, we can have a formula also. So I will do it in the later slides. Now this was the thing about this formula. Now how we'll use this formula? So to use this formula, we need to remember this table first of all. So here is that Z value. Z or Z value, you can write here Z also. So suppose we have Z is equals to 2, then it will have a linear structure in which the angle is 180 degree. Now if the Z is equals to 3, so this Z is also called a steric number also. So for Z is equals to 3, we have a trigonal planar. Similarly for Z is equal to 4, tetrahedral, then trigonal bipyramidal, and then we have this octahedral, that is SF6. So we can do one more example here to get the grasp of it. So let us do it for ammonia, sorry ammonia not, that's methane molecule, or BF3 say we have. So if you write the Lewis dot structure for BF3, so BF3 is how many electrons? So it is hydrogen, helium, lithium, beryllium, boron, carbon. Boron has 5 electrons, so it will be like 2, 3, so it will be 1s2, 2s2, and then 2p1. So if we see the number of means valence electron, it is 3. So 1, 2, 3. So I'm again doing this Lewis dot structure to get you things more clearly. Then we have the which molecule F. The F atom is here. F element is here. So it will need 1 electron. So it will share its electron from this BF3. Like this. And now BF3 will do the same. It will take one electron from each of this. Now if we write the formula here, so Z will be equals to 1 by 2 of number of valence electron, it is 3, charges are 0 again, and what is the number, what is the last term? So it was number of monovalent compound, so monovalent atom, so it is 3, that is 3 plus 3, it is 6, 6 by 2, we have 3. So we found out that we have a Z is equals to 3. So yeah, Z is equals to 3, that is trigonal planar. So in this way you can find the structure, or means the geometry of the given molecule. So you can do all this example by yourself for PCl5, then for methane, then for SF6, and see whether this formula works for all of them. So it will be a good practice for you. Now next, the problem came upon when we were seeing the angles that was according to the given structure. So if you see here, so we have some angles here. So like 180, then 120, then 109.5 degrees, then we have 90, 120. So they are for the perfect octahedral, perfect tetrahedral, perfect trigonal planar, and such perfect structures. But later on, when we see it for the ammonia molecule and compared it with this methane molecule, we see that there is a distortion of this ammonia molecule from the perfect one. So how is it so? So if you see that for methane, we have this 109 degree in 5 minutes. So you can write it also like this, 109.5 also, it is same degrees. So this is the perfect angle for this tetrahedral. But if we see it for ammonia, then it is 107 degrees. So it is less than the actual or the for the perfect one. So this was explained later by this Nylom and Gillip. So they again refined this VSEPR theory. So they took the consideration of repulsion for lone pair and bond pair differently to explain this. So what they said that, okay, so we have some lone pair repulsion, then we do have lone pair bond pair repulsion, we have bond pair and bond pair repulsion. So the means the extent of repulsion between these pairs do not remain same for all of this. So it will change variously. So it is maximum for lone pair. So lone pair will have maximum repulsion between them. Then comes the lone pair bond pair. Then comes the bond pair. So in this way, they try to explain the this distortion in the perfect structure. So what they said is that suppose we have this ammonia molecule. Now this ammonia molecule has nitrogen, this electron here. Now since these electrons are not shared paired, so it is between the one nuclei only, so they are close to the central atom. Now due to this closeness of this electron towards the central atom, there is kind of repulsion thing happening here. So there is kind of steric hindrance is occurring here. And to means stabilize the energy, so we do know that if there is more repulsion, then we have more energy as compared to the less repulsion one. So to bring down this energy, this bond pair move away from this lone pair, so that the distance between this lone pair and the bond pair decreases, so that the repulsion also decreases. So what does happen? So suppose you have something like a tripod stand like this, and you have one this line upon this. Now this line is pushing from all directions, so it is applying pressure to these three from all direction. From all direction, not from this upper direction. And due to this, they are moved inward towards each other. So they are mutually moving towards each other. So this lone pair is applying pressure on these three bond pairs like this, due to the repulsion between the lone pair and the bond pair. So we do know that this is the methane case, and they have also the repulsion between these two, but since it is a bond pair repulsion, and we know that the electrons are more towards here as compared to this one. So it is the explanation, you can say it is a very good explanation, that yes, since this there are also two electrons, here is also two electrons, but since they are shared between these two, so the electrons are more delocalized as compared to this lone pair, which is localized to this central atom and increasing the repulsion. Now this bond pair will apply pressure on this, or you can say force on this, less. Why? Because bond pair repulsion is less as compared to the lone pair bond pair repulsion. Now according to this theory, this will contract, and the angle, that is 109 degree 9.5 degrees, will reduce to 107 degrees, and we will get a distorted tetrahedral geometry. So similarly, for different compounds, we have different number of lone pair, and we do decide the geometry accordingly. So here I put up a table here to explain it. So it is like this. So we do have the parent shape, or you can say the shape also. Okay, so it is getting erased. Wait a minute. Yeah. So this is the molecular shape. This is the geometry, you can say. So parent shape is not generally used. This term is not used. So generally we have this geometry. Okay. Then we have this molecular shape. Then we have this picture here formed for both of this. Geometry. This is shape. So what is the main difference between the geometry and shape? So the thing is very confusing for most of the students, that in exams students are asked, okay, say the geometry or say the shape, they get confused. So so keep in mind that geometry is related to always lone pairs. So geometry is including both lone pair and the bond pair. So it is overall structure. But the shape is including only the bond pair. So this is the main difference between the geometry and the shape. Now, suppose we have a triangular bipyramidal shape, sorry, geometry, that is we are having for 5 value of z as 5. Now suppose one of this bond pair is replaced by a lone pair. Of course, then once it is replaced, then we do get a seesaw type of molecular shapes. You can see it clearly, looks like a seesaw. Now we have again a third type of shape, this shape, that is T shape. Now two lone pairs are replaced by this, two bond pair are replaced by this lone pairs. Now we have this linear. Okay, so let me explain it like this. So if you want, we can draw a clear diagram. Okay, so here it is, this lone pair. So we will see examples to explain it. That means to illustrate it, how is it so. Then we have X. So if you see here that the shape of the molecule excluding this lone pair is simply linear. Okay. Now if we include this lone pair as well, then we will get a trigonal bipyramidal. So this is the main difference between geometry and shape. And the way of calculation for geometry is that one. We know that one. It is Z is equals to half of valence electron plus negative charge minus positive charge. Then we have the monovalent atoms. And then we get the value of Z, and whatever will be the value of Z, then you will see the table, or you will must means remember this table always, and whatever comes, so you will assign the geometry accordingly. Then you have to learn the shapes accordingly. So according to which shape, then which we according to which the number of lone pair, we do decide this shape. So this is the thing here. So if we have a triangular bipyramidal, then we have no lone pair, then we have the same shape. So one lone pair, then the seesaw, two lone pair, then T shape, three lone pair, then linear. Similar thing goes for octahedral. So it is a perfect octahedral with no lone pair. Then one lone pair, then we say it as square based pyramidal. So it is quite clear here. So you can say it square based pyramidal. So one square is here and pyramid type of shape is forming here. Now for a square planar, we have two lone pairs. So one is up and one is down. So we have a square planar shape. Now let us move to our next slide. So we do have a question here. So the question says we have to find the structure of IF7. So how we'll find it? So we'll use the VSEPR theory simply. So it says use the formula. So first we will draw the Lewis structure for it. So if we draw it, so I has 7 electrons, 1, 2, 3, 4, 5, 6, 7. Now each fluorine has 1 electron to get to share so that it can complete its octet. So I'm not drawing the other means lone pair of this fluorine as it is not significant in case of VSEPR. So it is like this and it is like this. So it completed octet individually and quickly like this. 1, 2, 3, 4, 5, 6, 7. Now iodine will do the same. So you can see here clearly that we are seeing a hypervalent compound as the iodine is having a valency of 1 only to complete its octet to 8 sorry, but it is having more than 8 electrons. So it is an example of hypervalency. Now if we use the formula, that is Z is equals to half number of valence per electron. So it is simply 7. No negative charge, no positive charge. Then we have the number of non-valent compound, that is 7. That is 14 by 7, it is simply 7. So if you see the table, so 7 will be pentagonal bipyramidal. So this one is the correct answer. Because for octahedral it is 6, Z should be 6. For a square pyramid, if you see the example, so we are at the structure. So it is a square pyramidal, we have 4 plus 1, 5. Then triangular pyramidal is also 5. So the correct answer is 7, that is pentagonal pyramidal. Now we will move to this again question from Fajans rule. So it is said that you have to see that which one is having the most covalent character. So I have said earlier that first we will see the charge. So this is a plus 3 charge, this is a plus 2 charge, again plus 2 charge, and again plus 2 charge. Now the question is very simple here because we can see clearly that it has a maximum charge on it. So this one will be the answer. Why? Because we know that the electrostatic attraction of this cation, that is Al3 plus, will be more, so it will polarize that anion more, and we will get more covalent character according to Fajans rule. So this is the answer. So if you want, you can arrange this also in the increasing order of this covalency. So let me do this. So the second factor that it will decide is it is very size. So the size of anion is same for all of this because we are having a same anion, that is common anion, chloride anion. But if we see the metal here, that is the cation here, so we can see clearly that SnCl2 is having the largest size, so it will be the minimum covalency. Then we have FeCl2, then we have the MgCl2, and at last we have the AlCl3. So if you want, you can arrange in this order, increasing order of covalency, increasing order of covalent character. Now let us move to next slide. So we do have a question again here. So we do have to see that among the which species which to have the bipyramidal shape, which to have the triangular bipyramidal shape. So sometimes triangular bipyramidal is also referred to as TBP. So I can use this term sometimes. So let us draw the structure of each of this. So first let us do it for this Ni3. So if we draw this Lewis dot structure, so we're doing it for Ni3. Nitrogen has 5 valence electrons, so 1, 2, 3, 4, and 5. And we have this iodine here, so I'm only drawing this thing to do it shortly because we have to share only one electron for iodine. So it will be like this, simply this. So one thing you are seeing it here, that iodine or the higher means the atoms which are having the higher valency can change their valency from 1 to 2 to 3. They means they have variable valency. But if you see the means lower covalent, means lower atoms which are having the lower atomic number, they are not changing the valency so easily. So if you want, you can keep this. This is not always the case, but it's the case in maximum time. So if you want, you can keep it for the your mouth, that suppose we have some atoms. So if you want, we can have fluorine. So it will always have a 1. Then we have oxygen, which will always have a 2. Then we have this nitrogen also, which will have a 3. So for now, you can consider for all these 3 that yes, they will always have a 1. So there's some exceptional cases. So if there are some, I will deal with it later on. So this is the thing here. Now let us do it for nitrogen. So it will be like this. Now let us use this formula, that is Z is equals to half number of valence electron, it is 5. No charges, no charges. Then we have the number of monovalent atoms, that is 3. Adds 1, 2, 3. So what do you mean by what do I mean by a monovalent? So I mean that we are considering only those atoms which are having a covalency or valency of 1. So this electron is to only one electron is shared by iodine to this nitrogen. So we will only write those monovalent compound which have a oxidation state of +1. You can say that 5 plus 3 8, 1 by 2, that is 4 here. So 4. So we know that for TBP it is 5. So it is not the answer. So let us see another one, that is I3 minus. Yeah, it is I3 minus, yes. So let us do it quickly. So I3 minus 1, 2, 3. I3 minus 3, 4, 5, 6, 7. So if you write it here, it will be 1, 2, 3. Now it will grasp all these electrons back. So if you write the formula, then it will be Z half number of, this will be 7, this will be 0, this will be also be 0, 3 is 10. So it is having 5. So this steric number is 5 for this. So it will be one of the trigonal bipyramidal. So you can check this one by one and find the other compound to get a correct answer in all of these four. So let us move to another thing. So we do have a question again here. So I am telling you just the answer quickly. So if you want, you can do it. So you just have to decide that which one has a trigonal bipyramidal shape. That means you have to find out of these four compound which has the z is equals to 4 value. So I am doing it quickly here. So it is like this. So if you see that, yes, that is Ze. So Ze is a complete noble gas, so it will have 8 electrons. Then we have oxygen, so it is not a monovalent. So this one is means you can say a good example because it having no monovalency, means oxygen is not monovalent, so we will not count this atom here. Charges are also 0, so 4 monovalent fluorines are here. So 8 plus 4, 12, 12 by 2, which will be 6. So similarly, if you want, then we have 8, so no monovalent compound, so all 3 are oxygen. Then we have no charges, so it will be simply 1 by 2 of 8, that will be 4. If we consider it for this, then we have 8, so these 3 are not monovalent, we have only 2, it is 10, no charges at all, sorry, which will be 10 by 2, it is 5. So this is the correct answer. So it will also not be correct answer, so if you want, we can calculate it for now. So 8 plus 2, sorry, this one is wrong. So because, so you can say it is a multiple type, so you can draw it. So it will be 10 by 2, it will be 5. So two options are correct here. So sorry for not mentioning it here that it is a type of multiple select. Next we will move to another theory, that is the valence bond theory. So it is a very, you can say, complicated one. So most of students do not get an idea about this why this pi bond is format is pi p pi bonding is happening. So we'll deal with it more, you can say, more efficiently. So what happened is valence bond theory is that, so it describes the formation of chemical bonds using this overlapping of the atomic orbital. So atomic orbital do overlap over each other, and the area where the overlapping is happening between this atomic orbitals is having the maximum electron density. Now we have certain criteria for this overlapping. So we do say that yes, two things are overlapping, means you can say like this. So this atomic orbital overlap. So I'm considering just an example here, so do not take it literally. So suppose these two things overlap. So we are taking just two things here that are overlapping. So the area of overlapping will be like this. This will be the overlapping area. Now suppose we are having more overlapping. The extent of overlapping has increased. So it will be overlapped more. So what do you mean by this? You can see here clearly that the area of overlapping means overlapping area is more for this as compared to this. So this, by this we are meaning that what is overlapping. So I will explain it using atomic orbitals also, for but we are now considering some criteria which decide that overlapping. So I've just given you a brief means overview about this. So first is the distance. If the distance will be less between the atomic orbital less, so I'm using a down arrow, writing it here also. So as the distance will be less, so they will be more closer and overlapping will be more. If then the sizes. So when two atomic orbital combine, their sizes should be comparative. So it is not that we are taking an s orbital from 1s, then we are taking another s orbital of suppose the 5s, and we are trying to overlap between this. So due to this difference in size, there will be difference in their energy also. And since they are not properly you can say they are not properly means oriented due to this difference in energy, they do not overlap with each other. So size should be comparable for overlapping. Now next is the orientation. So for two atomic orbitals to means this overlap, there should be certain orientation so that they can come upon each other and get properly oriented. So there are some axis rule here, so we will see it. So how is it happening? using this thing that is given in NCRT. So one diagram, if you want, you can see it in NCRT. So overlap result in three types of overlapping, that is positive overlap, negative overlap, or zero overlap. This zero overlap. So we will see it this three one by one, and we will also see that how this orientation help in this thing. So suppose that overlapping is taking along z-axis, means the atomic orbitals, or you can say the atoms are coming closer to each other along the z-axis. So if you see the book commonly, they have this same orientation, means the atoms are considered to be coming along z-axis. Now since they are coming along z-axis, so suppose we have an atom here like this. This is the nucleus of that atom. So it will have pz orbital, px orbital, py orbital. So this will be py. Suppose this is the y-axis. Okay, this is, suppose this is the x-axis. Sorry, this is the z-axis, and this is the y-axis. Now similarly, if we do have another atom which have this same p orbitals. This is, you can say, px, then we have this pz, then we do have this py. We know that these three are mutually perpendicular to each other. So because three axes are mutually perpendicular to each other, and this lobes, you can say, are oriented on this axis, so they are also mutually perpendicular to each other. Now they will approach along z-axis towards each of them. So they will move like this. So if they will move like this, so the z lobe means the lobe of the pz orbital will combine with this lobe of the pz orbital, and there will be overlap between them. So by this I mean, what is the means orientation of this overlapping. So they are overlapping along the z-axis. Now since they are overlapping along the z-axis, then they should have the same phase also. So this phase does not mean that they are having a positive charge or the negative charge. It is just the sign of the wave function. So you must have seen this phase in this so-called you can say wave theory, means this physics also, that sound waves do have this phase. So if they are combining in the same phase, so they are increasing the amplitude, and if they're combining in the opposite phase, then their amplitude get cancelled and we get a zero overlap. So this is the same case goes with this you can say atomic orbitals, and atomic orbitals are nothing just but the wave functions. Okay, so if they are means combining in the same phase, so they will result in a positive overlap, and the electron density will increase in this region. So here is the thing, that they are combining along the z-axis. Now due to this combining along z-axis, so this it is getting overlapped very efficiently. So this is also along z-axis. So if you want to imagine like this, so you can see here that this one and this one will combine like this. Similarly, this one will combine with this one. Okay, so this will be the case. Now this px will combine on the sidewise fashion. So we will see that why this sidewise fashion resulting, and the this is head on head, you can say, because head and head are combining with each other. Then we have side by side overlapping. So two type overlapping also there based on this extent of overlapping, and this is the thing you can say the orientation of overlapping. So this results in positive overlap. Similarly, if that if they are opposite in phases, so this one is opposite in phase, so they are having a negative overlap as they has the opposite sign. So positive and negative, they get cancelled and we have a negative overlap, you can say. Then we have the zero overlap. So what do you mean zero overlap? So the difference between the negative and the positive, means negative and the zero overlap, is that you can see here clearly that this positive phase is overlapping with this positive phase also and with this negative phase also. So they both cancel each other and they're out of phase due to difference in orientation. So this is the example of out of phase, and this is the example of negative overlap. So in this fashion we have three type of overlap. So if you can see here that pz and pz are having a negative overlap also, then pz and s are having, then px px and py py. So and similarly we have px py. So if you see here px py, suppose we have a px py. Let me take a different pen. Okay, let us do it in board. Suppose we have px like this. So first of all, make it clear it in mind that it is not a two-dimensional figure. Okay, so it is not a two-dimensional figure. It is a kind of three-dimensional figure, which will have some part in all the direction. That is in x, y, z also. Means it is not just that it is kept on the board and it is flat. It is like a lobe. So you can think of it as a water droplet like this. So it is a water droplet up, and it is a down one. Then we have another one, that is py. Now another one, another means you can say nucleus is coming like this, and it is overlapping with this one. Now suppose we take like this and we take it like this. So we are taking the px and py. Now what will happen is that suppose it has a positive. So I'm writing it more clearly. Then suppose it has a positive one, it has a negative one, similarly it has a positive one, it has a negative one. Now when this positive will go towards it, it will overlap with this positive and negative as well, so there will be 0. So it will be 0 overlap. Similarly this negative will go, so it will go like this. So I'm drawing this here also, so it will be kind of like this after it combines with this px1. Now you can see here clearly, so it is not that much clear, so you need a 3D diagram to explain it, but I am making it more obvious so that you can understand it. This positive is overlapping with this positive and negative both. Similarly, this negative is overlapping with positive and negative both. So they are cancelling each other and we are getting a 0 overlap. So these are the three kinds of overlap we have. Now, this different type of overlap result in different type of bonds. So we have two kind of bonds, that are sigma bonds and pi bonds. So when we have a head-to-head collision, so we have seen it earlier that we are having head-to-head collision like pz and pz or pz or s orbital. Then we have the sigma bond formation. What are the characteristics of sigma bond formation? So it is formed due to the head-to-head on collision of atomic orbital. And the second as most important thing is that the sigma orbitals are always stronger than pi orbitals. Means sigma bonds are always stronger than pi bonds. So if you see this diagram here, so we have first of all s and s orbital, so they are colliding head to head. Suppose it is a positive phase, it is also having a positive phase. They will combine and form a SS overlapping, which is a sigma kind of bond. Now again, suppose there is a overlapping like this, then we will have this kind of, we can say sigma bond. Similarly, this one, sorry. So it can also have like this fashion, in this fashion. So suppose this negative, this positive are overlapping, and we get this type of overlap. I mean to say here that it does not matter that we are combining negative phase with a negative phase or positive phase with a positive phase. We will also always get a positive overlap, plus since it is a head-on-head collision, we will get a sigma bond here. So it is PP overlapping, SP, and this is SS. Now the second one is you can say pi means pi bonding. So why does it happen? So it is due to the sidewise overlapping. So you have seen earlier in the positive overlap that we can have sidewise overlap. So in this sidewise overlap, what happens is that we have a positive phase here, positive phase here, negative phase here, negative phase here. They do combine and forms a overlapping region between these two. But the main difference with two is you can see that this overlapping area is not that much. And we know that more is the overlapping, means if two atomic orbitals are overlapped more, the bond that is formed will be stronger. But in sigma we have this head on head, so it has a larger you can say overlapping area as compared to the pi bonds, in which the overlapping area is less. And after this they combine, they form this kind of hybrid orbital. So I will see make you understand this hybrid orbital in the later slides. So this is the thing here between the sigma bond and pi bond. And you can see in the all these examples that a bond is always forming that when there is a positive overlap. So a negative or a zero overlap never results in a formation of a bond. Now the next, the more important concept of this theory, you can say, it is the hybridization. So often children are asked in the question that, okay, tell the hybridization of this compound or tell the hybridization of those compound. So we'll see it how we do it. So what happens in hybridization? So we you can say combine this atomic orbital and of a single atom. Like if you have an atom, then their atomic orbital combine and they combine to form something called hybrid orbitals. And the number of atomic orbitals that are combining will be equal to the number of hybrid orbitals that are formed. Next thing is that the most important thing is that the hybridized orbital are always same in energy and shape. Yeah, this is the important point here. So if you form two hybrid orbitals, so they both will have the same shape and the same size and the same energy. So this is the main. So the hybridized means only we have the same energy. Now, what is the difference between this hybrid orbital and atomic orbital? The first one is that they are, you can say that they are formed by the combination of atomic orbitals, while atomic orbitals are independent itself. Next, the hybrid orbitals are more capable of, you can say, forming bonds, but atomic orbitals are not that much capable. Then, and why is it so? Because they are oriented, or you can say means having proper energy orientation after the combination, so that they can form bond easily. Now, all atomic orbital are not same in energy, while all hybridized orbital are same in energy after the combination. Now, this hybrid orbital that are formed, they are means oriented in such a way after the combination, so that it can lead to bond formation. The same thing is written here, that yes, hybrid orbitals are means directed in space like that to have minimum repulsion. Yeah, this thing also. So if this thing called the surrounding atom have to approach, the area should not be crowded, so that there should be no repulsion between the surrounding atoms. For that reason, the lobes are oriented of that hybrid orbital in such a way that the repulsion is minimum. Now, important condition for overlapping. So what are the things that we have to keep in mind while overlapping? So first of all, the orbitals are of the valence shell. So the orbitals of the valence shell combine and they are only hybridized. Second thing is that all hybridized orbital means atomic orbital must have almost equal energy for the combination. Now next, we will see that there is an excitation of electron. So this excitation of electron do take place in subcompound, but is not necessary for all the compounds. So if you found a CH4 molecule, then it will have excitation. Then in case of PCl5, we do not have an excitation such that. And the last and the most important point, so you will see some example in the next lecture of it, that all means it is not important that only that atomic orbital will combine hybridization which have a half filled orbital. Okay. So now when this atomic orbital combine, they can form different type of hybridization. The first one we will see is the sp hybridization. So what happens in sp hybridization? So in sp hybridization, one s orbital and one p orbital, they overlap to form this kind of shape. So it is sp hybridized. So this is the negative part, this is the negative part, sorry, this is the negative phase. So you do not need to show this phase. So one s and one p orbital of this beryllium, they will combine, this two atomic orbital will combine and form this type of hybrid orbitals, sp hybrid orbital. And then the Cl, that is having pz orbital, so they will come along the axis, so that there can be head-on-head collision between these two, and we can get a sp hybridized beryllium chloride and a linear structure. So sp has a linear structure. Now next, we do have this BF3. So what is the number of this atomic orbitals in the valence shell of this BF boron? So we know that it has 1s2, 2s2, and 2p1. So we have S and P. Now what happened is that, so if you see it here, that boron has 5, so 2 plus 2 plus 1, 4 and 5. Yeah, right. So if you see here, the S combines with two p orbitals to form this sp2 thing. So this is the sp2 hybridized orbital of boron. And now the chlorine pz orbital will come along the z axis. Similarly, in the earlier case it happened, and they will form a triangular planar type of shape. So if you want to remember this hybridization, so this is the thing we are getting it, so we are not knowing that which one atomic orbital will combine. So it will also be decided using that steric number. So it's a shortcut you can say. So suppose we have this steric number of 2, then we have the sp hybridization, so and then we have the linear shape. So these three are all combined you can say. Now if we have this steric number of 3, so it will have a sp2 hybridization, that is triangular planar, and we have a sp2 hybridization. Now next one we have this sp3. So sp3 hybridization can be seen in ethane and methane molecule. So what happened is that this in this sp3 hybridization, so if you want you can see it through this atomic orbital combination also. So if you write 1s2, then 2s2, then 2p2. Now what happened? The excitation of this electron take place during this hybridization. So we do have like this. Now the hydrogen atom which has one electron, they overlap. So we can have formed. So now this all atomic orbitals are now hybridized and has formed sp3 hybridized orbitals, and this each of these atomic orbital do have the same energy. Earlier you know that the 2s2 will have the less energy as compared to 2p2 using n plus n rule. You know that. But as they are combining and forming a hybridized orbital, now this all these four atomic orbital are having same energy. Now this all these lobes have certain this orientation like this to form a tetrahedron. Could we start? Student, for the interruption, the internet got shut down. So we'll continue with that orientation thing we are considering. So we have seen that yes, the excitation take place, and we do have this sp3 hybridized orbital. Then the hydrogen came in orientation, and we do this get this tetrahedral structure for this methane molecule. So same is the case of ethane molecules. I will show it later with an example. So now let us move to this sp3 dehybridization. So it is simple that one s orbital and three p orbital, that is px, py, and pz, they all will combine and they will give and with a d orbital to give this sp3d. Now the important thing here is that there are three d orbitals for 5d orbitals. Now which d orbital will combine? So I will show it now to explain it now. So here we do have a sp3 hybridization photo. So if you want that, yeah, we have to form only say sigma bonds here. So for two sigma bonds to form, the dz means the d orbital should come along z axis so that they can orient with this this s then this called pizza orbital to form this sigma bond. So it should have a head and a head collision. So there is only one atomic orbital that is oriented along, means there is only one d orbital that is oriented along that z axis, and it can only form sigma bond. So due to this reason, the dz square atomic orbital will be chosen for this TVP formation. So it will come along this, you can say that it can come along this z axis and form the sigma bond. So in this way, sp3d hybridization is formed. So in the earlier hybridization, we do have a thing what is S percentage. So I will discuss it in the last, after we complete all this hybridization. So we do have something different for this sp3 hybridization, means if you consider the bond length of this. So let me give an example. So if you take the PCl5, so if you consider this bonds are equatorial, as are this on this equatorial bond. So this bond is called the equatorial bonds, this three, this one, and this one. This equatorial bond are shorter than axial bond. Now why is it so? So you know that these three are present at 120 degree to each other. So if you see the previous chart of the TVP, you can see that it is a 120 degree angle. But if you see this angle here, between this axial and equatorial, it is a 90 degree. And since this angle is less, this electrons and this bond pair electrons are closer to each other. So due to this reason, they will experience more repulsion. To avoid that repulsion, this bond becomes longer so that the electron density is distributed more. So you know that if a charge is accumulated more in a place, then it will have a more force of attraction. We have seen that thing in the Fajans also. Now for the similar reason that we increase this bond length, so that means the atoms, the compound increase its bond length so that the charge is not accumulated on one place and we get less electrostatic repulsion. So for this, the cause of 90 degree angle, this bond become longer as compared to the equatorial one. So you can say that equatorial PCl5 bonds, PCl bonds, so equatorial PCl bonds are shorter than equatorial axial PCl bonds. So axial bonds are longer. Now there is an outcome of it. So if you want to know, then I can explain it. So if it is in this fashion that there is an outcome of this is that suppose we have an example like PCl3F2. So let us take a different screen for it. So like we have an example, we have PCl3F2, and outcome of this elongation of bond is that the electronegative element like fluorine prefers to stay on the equatorial position as compared to this axial position. So we can have a common thing like that, more electronegative thing, or the thing which have more electrons towards it, are on the axial bond or on the axial bonds. Why is it so? So suppose this is the PF3 now. Now this bond will be more polarized and electrons are attracted more towards the fluorine because it has a larger electronegativity. So the electrons will move closer to this fluorine. Similarly for this fluorine also. Now since the electrons are moving closer to fluorine, there is less electron crowding around this central atom here. Okay. Now since it has a less crowding, to make that less crowding, this electrons move here. Now in place of that, if we have Cl, then electron will move less as compared to this movement, and it will avoid less repulsion. But now since it has fluorine, the electrons will move more closer towards this fluorine as compared to chlorine, and there will be less repulsion between this bond pair and bond pair. So two things are here. So first of all, the bond length of PCl5 of means axial bond length is more than the equatorial bond length, And if we do have a means electronegative thing or a thing called something like negative thing, the negative carrying charge or electronegative compound, then they are present on the equatorial part. Similarly, if we have a lone pair along this, they will be also present here. Sorry, here. Why is it so? So the reason is very simple. So if they are present here, then they will, you know that bond pair repulsion is less than lone pair bond pair repulsion. So if we are keeping this electrons here, they will experience more force, means more repulsion from this bond pair, as the 90-degree to each other. So due to this reason, so they are 120 to each other. They are kept on this equatorial thing. Okay, so this is the means a good concept to remember. So if you want, you can. So it is very important. If you not want, it is or means important only. So you have to remember this. So these are the three means you can say uniqueness of this sp3d. Now next we will move to another hybridization, which is sp3d2. So I will make it more in a more short way. So in this 1s 3p and 2d orbital will combine to form this sp3d2, and it will have a octahedral shape, and all of these angles are 90-degree to each other. So this is 90-degree to 90-degree, here also 90-degree to each other. So if you want, you can calculate the number of 90 degrees. So this kind of questions do come. So you have to calculate the number of 90 degrees for an octahedral bond. So it is 1, 2, 3, 4 for this bond, then 1, 2, 3 for this bond, and then we have this 1, 2, 3, 4. So 4 plus 4 plus 4. Then we have 4 3 4 3 12. 12 90 degrees are there in the octahedral compound. Now we have to find the hybridization in alene system. So if you want, if you don't know, alene is something like this. So it is the sharing of electron pattern, means a pattern of electron sharing in alene. So you can see here. So if you want, you can calculate it. So half the number of valence electron, that is 4, plus 0 charges. Monovalent atoms are 2. So it will be 4 plus 2 6. 6 by 2, that is 3. So it is a sp2. The type of hybridization of carbon R means what type of hybridization it will have. So it is sp2, so it will be sp2. It is similar to this. So if you want to calculate for this Z, then it will be 1 by 2, it is 4 minus plus 0 minus 0 plus 0. No monovalent means hydrogen are not present on this carbon, as is both carbon are bivalent. So it will be 0. So 4 by 2, 2, which is sp hybridized. So this one is sp hybridized and this one is sp2. sp2, yes. So this is the answer. Now we have a different question here. So it says that we have to determine the hybridization of boron in this thing. So this is a conjugate bond. So those who not know the structure, so it is a direct question. So you must have say known the concept of conjugate base and conjugate acid. Base and acid. So here you can see that boron is electron deficient. We know that it is a hypovalent compound, and nitrogen is having electrons in the outermost orbit. Means lone pair. It has a lone pair. Now this nitrogen will donate electron to this boron to complete its octet. This is hydrogen or nitrogen, and this is the complete compound we are having here. It is called an adduct. ADDUCT, adduct. Now you can see here clearly that boron has 1, 2, 3, 4, 4 electron pairs here, or you can say 4 steric numbers. So the hybridization of boron is changing. So initially it will have sp3, sp2, then it will change to sp3. Then this is the answer, sp2 to sp3. Sorry, so this is wrong written here. So it will be sp3 to sp3. Now next we'll move to dipole moment. Okay, so we are out of time here, so we will deal this dipole moment tomorrow. So thank you for today's lecture.